So question 20. In a crystalline material, planes of symmetry are labelled using triplets for integer numbers of the form HKL. E.g. 100 is equivalent to 100. Okay, so not numbers, just some stuff. It doesn't matter what they mean. It is possible to determine these for multiple planes of symmetry. From the knowledge of several such triplets, the microscopic structure of the material can be inferred using the following rules. If for all planes of all positive integer values of HKL are possible, then there's a simple Q lattice. Okay. If for all planes all positive integers, okay, so if we have HKL bigger than 0, it is then a simple cubic lattice. If we have H plus K plus L equals 2n, where n is positive, then this is a body-centered cubic. And if H, K, L either all even or all odd, it has a face-centered cubic lattice. Okay. And it says, note 0 is an even number. So during the analysis of the data from such an experiment, the following 4 planes of symmetry were found. 111, 200, 220, and 311. Okay. What type of lattice did the material in these experiments have? So I'm going to write 111, 200, 311, and 220. Okay, this is part A. So basically what I'm going to do is I'm just going to work out which one of these have which. So 111, this is all bigger than 0, so this is a simple cubic lattice. So it has A. Do they all add up to an even number? No, they don't. Add up to 3. So it's not a body-centered cubic. All even or all odd, it is. So then it's a face-centered cubic, C. So now for 200, they're not all bigger than 0, so it's not A. They all add up to an even number, so it has B. And they are all even, so it is C. So now 311, they don't all add up to an even number. They're all bigger than 0, so it has A. They're all odd, so it's C. Then 220, we have not all bigger than 0, so not A. They all add up to an even number, so it has B, and they are all even, so it is C. So now, looking at all of these, you can see they all have in common C. So that means that it is C, which is a face-centered cubic. All right. So part B, in a material with some form of cubic lattice, the distance between the planes of symmetry is given by D equals A over the length, where A is the constant length, that is usually the order of a fraction of a nanometer. Determine the best estimate for A. Okay, so we want this. Can I move this? Okay. So now, what we have to do is we're going to have to work out our values for A for all of these things, and then we're just going to average them, and I'll give us our answer. So we know that A equals D square root H squared plus K squared plus L squared. Let's just get a calculator. So our value for the first one is going to be 0.224 times the square root of 1 squared plus 1 squared plus 1 squared, which is actually just 3. Okay, and this on the calculator is 0.3880. Okay, so A2, we have 0.195 times the square root of 4. So just like basically doubling that, we get 0.39. So A3 we get 0.137 times the square root of 2 squared plus 2 squared, which is 8. And this equals 0.3875. I'm just giving it to 4 decimal places, because I think in the question, did it ask? No, but these are all to 3 decimal places, so we're just going to give it to the amount that is said. So 4 decimal places will be plenty. So A4, this equals 0.117 times the square root of 3 squared plus 1 squared plus 1 squared, which is 11. 0.117 times root 11. Okay, sorry, just checking if the microphone's on. This equals 0.3880. So now, averaging all of these up, we get A equals plus we get 0.389 to 3 decimal places. So that's B. So now part C. A cube of the material has length L in each dimension where L equals NA, and N is a very large number. Pressure is applied to opposite sides of the cube. The volume of the cube remains constant, but one of the cube's dimensions reduces to a length of L prime equals 2/3 NA. What is the new length of the deformed object in the other 2 dimensions? Okay, so wait, what is the new length of the deformed objects in the other 2 dimensions? Excuse me. So first, we have a cube with like L sides. So this is L, L, L. So we know that the volume equals L cubed, which equals actually N cubed, A cubed. And then after the deformation, we know that it's just applied to 2 sides, I believe, to 2 opposite sides of the cube. So the volume remains constant, but one of the is reduced. Okay, so then after, the volume is constant, so we know that all of the sides have to change. If the pressure has been applied like on this side, we're going to say this equals 2/3 NA. And then this, we're going to say this is the new length x. So we know V equals x squared 2/3 NA. So we know that these volumes are equal. So just setting them equal, then we can work out what x is. So we have x squared. Firstly, we can divide through by this and this. So x squared equals 3/2 n squared a squared. So we then know that x equals root 3/2 NA, which is actually L from before L equals NA. So this equals x equals 3/2 L.